In this video, we're going to return to our earlier analysis of common families of functions and practice applying the skills or the rules that we learned there and connect them always back to the area interpretation of the integral. One of the properties we identified when we talked about converging integrals, and again remembering that that corresponds to a finite area under the curve, is that we first of all have to have an integrand that heads towards zero. If we're talking a function of t, if we had a function that went up at all, then the area would certainly be not finite or infinite as we get further and further to the right. So we have to have an integrand that goes to zero. But it's not sufficient to have that. We have to have that, and in addition, it has to approach zero in a way that's somehow faster than 1 over t. So if this is 1 over t, we know that the area underneath that is not actually finite. It diverges. But if we had a separate graph that approached zero faster, it got down lower sooner, then this area would be finite. Or the integral would converge. With that in mind, let's take a look at this question here. Would the integral from 1 to infinity of the negative exponential written here converge? Or another way to ask that, is the area represented by that integral finite? Take a moment to think about that, and then we'll check in. All right. The answer here would definitely be yes, because any exponential decay is something that's going to go towards zero faster than a power of t. It's something like exponentials grow more quickly than polynomials, and negative exponentials shrink more quickly than 1 over polynomials. We can also confirm that with a quick calculation. Our integral here, let's call it I, can be replaced by, must be replaced by, as the first step, by the definition. We're going to integrate not to the infinity quantity, but up to b, and then we're going to take the limit as b approaches infinity of that. Now we have concrete values in here. We can actually evaluate this integral. We have the integral of e to the negative 0.1t is the same exponential again, but we have to divide by that coefficient so that when we go the other way, if we differentiated, we'd end up canceling out and getting just the simple exponential back. And then we also have our limits of integration, 1 and b. Then we're still going to ask what happens to all of this as b approaches infinity, but we're going to plug in our value. First b, e to the negative 0.01b minus, we plug in the 1, e to the minus 0.01. Squeeze that in on the end there. Now we can assess what happens when b approaches infinity. We just have an expression, and as b gets larger and larger, we have a negative exponential, so this entire term approaches 0. So we end up with a double negative, that's a positive, e to the negative 0.01. And this is finite, and so the integral converges. There we are. Let's take a look at some other examples. Now consider the integral from 1 to infinity of 1 over t squared. Is the area underneath that, or represented by that integral, finite, or does that integral converge? Pause the video and take a moment to think about that. All right, the answer here again would be yes. And we can think about that through the calculation, but we've already seen that before. Let's remind ourselves just of what the criteria was, though. If we have the graph of y equals 1 over t, its area, represented by the integral from 1 to infinity, would not be finite. But 1 over t squared, they'll both start at 1, 1. But by the time we get to 2, 1 over t squared will be smaller. And if we go to 3, it would be 1 over 9 instead of 1 over 3. We would definitely approach 0 faster. 1 over t squared approaches 0 faster than 1 over t, and that tells us that the integral represented by that converges, or is finite, has a finite value. Alternatively, the other way we approached this was to look at general power is 1 over t to the k, and we said that converged for k larger than 1. The bigger the exponent in the denominator, the faster this graph will drop, the smaller the area will be, and so the more likely it will be to be a finite area. All of these criteria lead us to this integral converging. What about the example of 1 over root t? Is that area finite, or area represented by that integral finite? Does that integral converge? Pause the video, take a moment to think about that one. All right, in this case, the answer would be a no. Again, we have our borderline case for powers of t. It's 1 over t. But if we consider the graph of 1 over root t, by the time we go to 2, this graph would be at 1/2, but root t is actually higher than that. It's 1 over root 2, which is 1 over 1 point something. It's over a smaller value. And so the graph we get for this, for y equals 1 over root t, is above our threshold function 1 over t. And so this area here, larger than the 1 over t area, but that's already an infinite area. And so we would get an infinite area for this integral. It does not converge, or it diverges. Using our rules about powers of t to some exponent, in this case here, we have 1 over root t. That's 1 over t to the 1/2. That was our k equals 1/2. That is less than 1. It's too small a power. The graph does not approach 0 quickly enough. So that was the other way to arrive at the conclusion that this integral diverges. So again, a few ways to reason through this kind of problem. In addition, we could always go through the actual calculation for this. It only takes about 3 or 4 lines of calculation to reassure ourselves that, yes, this integral will lead to an infinite limit, and so we have an infinite area being represented there. In terms of expectations, what we would expect is that you would be able to apply these kinds of logical criteria to a particular example for a particular infinite or improper integral, and also then back that up with a calculation as well, correctly applying the definition of the improper integral to get an exact value if we can actually get a convergent integral.